Welcome to Shrinking and Stretching, Unit 2, Manipulating Graphs. We'll again start with the same slide. Today we are looking at the A and the B. Okay, so the A is going to stretch vertically, so this says, okay, affects the y coordinate. It's going to stretch and shrink things, our functions vertically. And B, x coordinate, is going to stretch and shrink our x coordinate, coordinates horizontally. So our graph horizontally. So one thing to remember as we move is the B is a little bit weird. There's a little bit of a trick to it, a lot like the H, how we had to do the opposite of that sign when we move stuff. Same thing's going to be here when we stretch and shrink. We have a little quirk to the B. If you look here, you notice that we have two graphs. Okay, the first graph, if you look, okay, this is getting stretched vertically from G to F. Okay, I'll just start with G. It's getting vertically stretched to F. Okay, and it looks like by a factor of 2, because if this crosses the y-axis at 4, and it gets stretched all the way up to 8, okay, it looks like it's got a vertical stretch of 2. The other graph, okay, if you imagine this, thinking about grabbing the sides of this and playing it like an accordion, okay, stretching and shrinking. Looks like if we start at the red graph, okay, the lighter graph looks like it's getting pushed together. It's condensing, okay, it's shrinking. And it looks like, well, if this crosses the x-axis around 6, okay, and there's kind of one wave gets completed and it crosses the x-axis at 6. Well, that same spot is or -6. Same spot's at -3 here. Okay, again, so that looks like it's getting shrunk by a factor of 2, or stretched by a factor of 1/2. Okay, so if you think of stretching by a factor of 1/2, that'd actually be making it smaller, right? Multiplying by a fraction makes things smaller. It's being stretched by a factor of 1/2, and that's going to be important here in the future. Okay, for the rules. The rule for our first situation, okay, for our new function, if we take the parent function and multiply it by a, okay, our rule, well, as we know from the graph above in blue, what changes is the y-coordinate. So the x stays the same, okay, and the y-coordinate gets multiplied by a. So I'm going to write it a times y. Okay, so what's happening there is that the graph is scaled or stretched. I'm going to go with the word stretched. Stretched vertically by a factor of a. So all that to be stretched vertically, all that has to change is the y, and we're just multiplying the y by a for all the coordinates. For the second function form, so that's the graph to the right that's got the red curve, it's a little bit trickier. Yeah, our rule, actually the y stays the same, and because the b is inside of the parent function, so it's right next to the x, what we actually do is we multiply our x by a factor of 1 over b. Okay, it's a little tricky. We take 1 over b and then multiply that by our x. And what that does is that stretches horizontally by a factor of 1 over b, like you see there. All right, let's look at this first example. Real quick at the top, it says, just a reminder to remember a few things. Okay, first, is that scaled factor, is that inside or outside, okay, of the parent function? So is it right next to the x or not? And then remember to write the rules and to think specifically about what the x's change, because remember we have that 1 over b factor. That's a little bit tricky. And of course, just follow the rules when you're transferring the points. So this example says use a table to identify points and then sketch the graphs of f of x equals square root of x and g of x equals 2 times f of x. So f of x is the square root of x. I'm just going to pop that in there, our parent function, and go ahead and give our regular table for square roots. Okay, there are the x's because those are of course square rootable. Square root at 0 is 0, square root of 1 is 1, and so on. All right, now we can start thinking about our rule. And if we look at g of x, that's 2 f of x's, so 2 square roots of x. Okay, so that's our new rule. And we got to figure out what's actually happening here. Well, we're multiplying by 2, so that's on the outside. That's not inside next to the square root next to the x. That's on the outside. So that's only changing our y's by a factor of 2. I'm going to multiply by y's by 2. The x's stay the same, so I'll go ahead and fill those in. But the y's are different. Okay. Multiply my first y by 2. And that gets me 0. My second y by 2. And that gets me 2. And so on. All right. And then real quick, I'll just graph both of them. Okay, if I graph the parent function, you should be used to graphing these. Okay, there it is. 9, 3, right there. Now if I graph the scaled version on top of it, it'll look a little bit different. And there's a scaled up version. We just stretched everything by a factor of 2 vertically. Okay, all the y's just doubled themselves. All right, similar here, graph f of x equals x squared, and then graph g of x equals f of 3x. Okay, where again, that scale factor is inside, or unlike the last one, excuse me, the scale factor is inside next to the x. But first, let's talk parent functions. The parent function is x squared, and you can go ahead and fill in the table for that. There are the usual y's I use for x squared. Excuse me, the usual x's I use for x squared. And there are the usual y's. Now I'll go ahead and graph it. And there is the parabola that we all know and love. Okay? So let's talk the new function now, g of x. Okay, well that's just our x squared function, but a 3 multiplying by 3 in the middle. So I got to put my 3x in there and then square it. Okay? Now we need to write a rule. When there is a multiplication inside of the function, okay, like this is appearing inside of the squared, okay, that changes our rule a little bit. We have to worry about how that 1 over b scale factor. Okay, so and then if it's inside as well, we're stretching horizontally. So our new rule, the y would stay the same. So y's are going to stay the same. We don't have a number appearing on the outside of our function, only on the inside. And our x's are going to get multiplied by 1 over, in this case it's 3. So 1/3 x. An easy way to fill in the x's, okay, multiply by a fraction, especially if there's a 1 on top, okay, is just to go, well, -2 times a third is -2/3. -1 times a third is -1/3. 0 times a third is still 0. 1 times a third is a third. And 2 times a third is 2/3. And of course, the y's stay the same according to our rule. So 4, 1, 0, 1, 4. If I graph that, okay, this is pretty interesting. It's going to be hard to work in the thirds, okay, but this should condense my graph. Okay, if I'm multiplying by a third, that's making things smaller. Okay, so the graph's kind of condensing in on itself. So I'll go ahead and graph those points. And there we go. We have a parabola, but it kind of got skinny. Okay, it's like we took and pushed it in from both from the left and the right side. We condensed it, in this case by a factor of 1/3. All right, example 3 and the last one for this slideshow. Looks like we're going to graph two functions again without using the calculator. So let's graph both f of x equals x cubed and then the new function, which is 1/3 x cubed. So we're going to call x cubed the parent function, of course. Write that in there. Then I'll go ahead and put in the usual parent function table. Okay, there it is. Now I'll go ahead and put the y's in. Okay, that shouldn't be a surprise to you. Okay, that's just parent function in the table for f x equals x cubed. All right, let's go ahead while we're here and write in the new function, which is a 1/3 times x, all of it then cubed. Okay, so that 1/3 is like next to the x, that's a b. All right, and for our rule, we of course have to write it as 1 over b. In this case, it's already a fraction, so we just flip the fraction. Okay, so we multiply our x's by 3 over 1, or just 3, if you'd rather. I would rather, so I'm going to change that to 3. Oh, hold on while I go and rewrite everything we just did, because I accidentally erased it. All right, and then it's back. Okay, now I'm going to go ahead and write, we can flip the fraction to be 3 over 1, which of course can be just be 3. And since it's inside the parentheses, that 1/3, we're going to multiply that by x. In this case, there's no number outside of our parentheses other than the exponent. So we'll just keep the y by itself. And I need to do the transfers. Okay, so I need to multiply all the x's by 3. Negative 2 times 3 is negative 6. Negative 1 times 3 is negative 3. And so on. And for the y's, according to my rule, I'm keeping the y's the same. Okay, so I'll just fill those in real quick. And there we go. All right, so we just multiplied the x's by 3. So I'm going to go ahead and draw the parent function very fast. Okay, and then we need to graph our new points. And we just have to go ahead and put all of those individual points on the graph and then give the curve. Okay, there are the points. And this is a good example. I like this because you can really see that each red point just got bumped by 3 a little bit further away from the y-axis. Okay, it just got stretched out by a factor of 3. Okay, so if it was a 1, now it's a 3. If it was a 2, now it's at 6. So everything just got stretched by a factor of 3 left and right. Now I'll go ahead and just draw the curve so you can see the final graph. Okay, and there it is. Now I did go ahead and I had to fix this point right there. I accidentally drew it too narrow previously, but now it's good. Okay, and yeah, there we go. Vertical or horizontal stretch by 3.